What I want to share is, what are we doing in advanced manufacturing? First of all, why is advanced manufacturing an energy issue? How do we wind up dealing with some of the technology development? What's our goals? And how this ties back to energy efficiency. So the Advanced Manufacturing Office, you look at one of the issues in manufacturing is manufacturing around clean energy products. And one of the things the EERE started doing about 4 or 5 years ago was the recognition that manufacturing is getting really, really important in the clean energy sector. So why is that? You've got a number of technologies, whether it's solar cells, whether it's batteries, whether it's wind, whether it's fuel cells, whether it's electric vehicles, whether it's driverless cars, where we can argue, is this going to wind up hitting parity with the existing technology in 2016? Is it going to hit it in 2018? If we're at that point where we're having that debate, we really have a transformation on our doorstep right now. Because we're at the point where we're going to hit a crossover point, not only in our lifetimes, but in the next decade on these technologies. So why does this matter? Well, if you look in history, those points where you hit a crossover point relative to a technology for how it's being done, where you do that first manufacturing at that point, winds up not only driving you across the point to adoption, but also that becomes the framework for economic activity in that area, in that place, for the next century. So the model here is Henry Ford. Henry Ford did not invent the electric vehicle. He did not invent the internal combustion engine. Diesel and Otto did that. That's why their names are on the cycle. What he did was he figured out the manufacturing process so that relative to the incumbent technology, which was walking or riding a horse, that you could wind up actually more cost effectively drive to achieve your goals. Where you wound up doing that crossover point, that first manufacturing, was right around the Detroit area at the beginning of the 20th century. From that, the next 2 or 3 generations of economic activity was really built around that Detroit area because of that. It builds in the ecosystems, it makes things happen. So we're really focusing on this because the other trend we're fighting against right now is really over the past 25, 30, even 40 years, my professional life, it wasn't me that did it, but my professional life, we've heard this story, it's okay that we're not manufacturing anymore. Because what we're going to do is we're going to constantly innovate, and then we can let it be manufactured anywhere in the world, but we're going to be the ones that are going to be the innovators, and we're going to invent the next thing. Well, what we discovered when we wound up doing that is not just the overall manufacturing, but that first pilot manufacturing is a real strong forcing function connecting back to your research ecosystem. You find that here in the Valley all the time. 18% of the jobs in the Valley still are manufacturing jobs. People that don't think you're manufacturing here, and it's all that first pilot manufacturing. It's the pilot production lines. It's Tesla building their first vehicles. It's Intel standing up their capabilities. It's NVIDIA, folks like that. Because that becomes a positive feedback loop into places like Stanford, into places like Berkeley. So we're researching the right thing going forward. Uh-oh, I pushed some button and I have no idea what it is. Help? So that must be the cube. So I'm gonna just keep going. Okay, keep going, okay. So the thing that we wound up finding is not just in economic activity overall, but in economic activity in advanced technologies. By having that strategy, we had about a 20-year decline in advanced technologies. These are computer chips. You look at software design centers that are actually moving out of the Valley now, right, as well. That becomes globalized as well. What's the change as well is we wind up finding, if I can get the data here, that we wind up actually having a decline in the manufacturing imports versus exports in advanced technologies as well. And so it's really important for us to look at it and use technology, which is the strength of us, right? It's what innovation in the US is all about, is taking technology, taking the brightest minds to address that advantage problem we wind up having, that challenging problem. So that we wind up being in a place where you've got the best productivity adjusted labor rates in the world, right? And that's the thing that the US really focuses on. So within that, then the Department of Energy, you look at how does energy play into this? Well, energy in manufacturing sits at the nexus of 3 things. One is, of course, the environment. How we use energy in manufacturing is important to the environment around us. About 25 to 30% of all the energy used in our economy goes into the manufacturing sector still. So how we can most efficiently do that drives the cost effectiveness, it drives the economy, it drives the environment, it also drives your security. Your own future, really, if you don't have some manufacturing base, you're in less control of your own future as a society. So how we wind up bringing those three things together is really important. So the Department of Energy is part of, I don't know, is the screen coming back up at some point?
It's coming. For some reason it turned itself off, but it has to cool down before it can turn
Oh, okay, thank you. Okay. So this was recognized in the administration in two areas. One is in our climate action plan. Built into the climate action plan is the idea of innovation and innovation in the manufacturing sector. It's a key to wind up reaching our climate goals. I'm just going to take an aside here because we were talking about this earlier relative to what came out of Paris. The framework for Paris is that we wind up having climate goals that we're setting globally. And then we're in a position where we can ratchet that up over time based on the state of technology. What that means is as an international agreement, we're at the point where we are betting on innovation, right? It's betting literally on all of you to wind up addressing this problem. So that's why the Department of Energy is actually investing in these areas, because by innovating, we can take the technology coming out of the great labs, the great universities, working with the great students, the great entrepreneurs, the great business people out there that can wind up moving those innovations forward, getting them as quickly into the marketplace, and then innovating on top of those innovations as well. So based on the Climate Action Plan and then the National Economic Council's plans around manufacturing, we within the Department of Energy actually went through a process over the past year called our Quadrennial Technology Review. I think a number of people in the room actually contributed to this, wound up helping out with peer reviews. What this did is we openly engaged people across industry, across universities, had a lot of input, RFIs, workshops, all that sort of stuff, to come together and say, what are those technology areas that if we wind up pushing those forward, we'll wind up getting breakthroughs in energy and we'll wind up achieving our goals. How do we focus our minds around those problems? Chapter 6 of that is actually advanced manufacturing technologies for clean energy. And it identifies 14 technology priority areas that I'm going to get to in a second around manufacturing and focusing on that. How that then comes down into the advanced manufacturing office really drives into two functional areas we wind up working on. One is how we develop energy efficiency technologies that are broadly applicable across manufacturing. So as you develop these technologies, it's not just helping one sector, but it's helping energy efficiency at many sectors. Probably the biggest emerging issue in this area you are at ground zero for right now, which is information technology in manufacturing. When I went through school, you talked about manufacturing in terms of materials and processes. There's a third leg to that stool now, which is materials, processes, and information. And so how you use that informatics so we can actually make better decisions out of the data you're getting around your manufacturing processes. It's a huge research and development area right now. You know, bringing in whatever buzzwords you want to use, Internet of Things, you name it, the advanced sensors and controls, how you bring those into the manufacturing sector really winds up mattering. So the other area, I should say, within the office is developing platform materials and process technologies that you can then apply for making these clean energy products. So it's not just the energy efficiency in the kind of energy intensive industries, but it's looking at how we wind up developing platform technologies for next generation ideas of how we can actually make those materials. So the other thing, for those of you who are students out there interested in a really hard problem to work on in energy, it's working in the manufacturing sector. So why is that? If you look at the manufacturing sector from an energy perspective, every form of primary energy winds up coming into the manufacturing sector. You don't have a silver bullet. You wind up having you have a huge technological challenge and a diversity of technological challenges to work on. If you can't find a problem to work on in that area, you're not really looking hard. The other issue is generally manufacturers and businesses, because there's a strong profit motive, actually are fairly efficient relative to the economically available technology. You know, you look at behavior on this, profitability is a huge behavior driver on that. So you find the manufacturing sector actually being one of the more energy efficient sectors in terms of energy going into delivered products versus into waste heat. So it's a really hard problem to work on. It's a worthwhile problem to work on. And it's also an area that's really essential to work on. So if you look at energy in manufacturing, about 2/3 of the energy in manufacturing goes into a handful of industries that we call the energy-intensive industries, that we still depend on for the daily lives that we wind up living. You've got primary metal refining, you've got petroleum refining, you've got chemicals, you've got pulp and paper, you've got food processing, and you've got glass and cement. I'll tell you a problem, a meta problem to solve. There's a huge amount of energy we wind up using as a society just for drying stuff out. If you can figure that out, that's a huge problem. How do you wind up addressing it? We also have a set of energy-dependent technologies out there. These are emerging technologies that have a high intensity of energy that you wind up using for what you make. But the only reason they're not an energy-intensive industry, the absolute number isn't big, is just because that technology has not been adopted widely yet. The classic example I would look at here is carbon fiber technologies. I think there was a question over here about energy intensity on some of the technologies we're looking at for the automotive area. Carbon fiber, it's T to the fourth. It's a very high temperature you wind up processing carbon fibers on. It's a very energy-intensive process per pound of material you're making. How do you wind up driving that energy out of it? I will also point out that it's a chemical reaction process that ultimately is exothermic. So if you think about it, we should be getting heat out of that process, not putting heat into it. So how do you wind up doing that? And you can think about things like, solar cells, materials joining, batteries. How do we wind up driving down the energy in those? Then the last area that we're looking at on energy is this connection between energy and water. And I know Stanford actually has an ERC on, how many people here are working on the ERC that's related to fresh water? Anyone in here that's part of that? So how you wind up using energy for water and how water is important to the energy sector. So the Department of Energy published this energy water nexus problem report, and it's highlighted here where you're looking at where energy is used going through the system and where's water used and where they're connected. A key element here you look at is the amount of energy that's actually used for public drinking water. And if you consider what is pipe parity, that's the equivalent of grid parity, where what we really want to be able to figure out is a technology where you have the exact same energy cost, the exact same economic cost, exact same carbon cost, but we're able to deliver that water out of any feed source and getting it drinkable. That's the ultimate goal we're trying to drive towards. There's a range of technologies you can wind up getting to. If you look in the FY17 budget that was just published last week, the Department of Energy is taking this on head on, and we're looking at things like putting together research consortia around this energy water nexus problem and how you can wind up really getting into that integrated systems problem to address that. We wind up pulling together, I should say, it's the Department of Energy. One huge thing, by the way, for students that are doing your research, the Department of Energy runs something called the Energy Information Agency. Do not underrate the importance of this. It becomes the unimpeachable source of data on where do we wind up standing relative to energy being used. Every 4 years, we actually do a detailed survey across the entire economy of what processes energy go into. So that's an area we wind up working on. We also do studies looking at things like where's the technical potential for things like chemicals and petroleum and steel and things like that. So a bunch of work in that area. As I mentioned earlier, our quadrennial technology review, we identified 14 technology areas, broke them into those two categories of platform technologies and emerging and energy efficiency technologies, where if we wind up addressing them, they can actually make step changes across the economy in manufacturing. And the reason this thing is that spider web in the middle is you find it's a connection of those technologies. It's information technologies between sensors and controls, additive manufacturing, the development of new materials, new roll-to-roll processes, chemical process intensification. All of those are opportunities where we can wind up driving innovation on this. We then break this down into the office itself, and we wind up saying, here's where we can wind up having our focused R&D efforts we wind up working on, so that then we work with folks like you to say, hey, I've got a new idea. Here's how we can wind up working together on this. Now we've got 3 ways we wind up working with, and I'm just gonna cut through this, working with folks. We have individual research and development projects. At the heart of it, we are a research and development office. working on energy efficiency for the manufacturing sector and energy technology, clean energy technologies. We have R&D facilities. So these are research consortium that we wind up working on. The highlight of this is we're actually within the Department of Energy, the folks that are rolling out the series of institutes called NNMI Institutes, National Network for Manufacturing Innovation Institutes. These are place-based innovation facilities where you bring together researchers that come across the supply chain so they can all wind up working together on a common set of problems that by addressing those problems will wind up moving things forward faster. And then we also do technical assistance, which is, I think back over here, someone was asking, what's the sub-national efforts we wind up doing? Well, these are areas where you've got a technology invented. We just need greater dissemination, and we need greater buy-in from industry to wind up getting that adoption or working with states around those things. So it's providing technical support around things like combined heat and power and energy efficiency practices. So we wind up running those sort of programs as well. I'm gonna highlight them real quickly here. We've got our Better Plants program. We've got our ISO 50001, which is a framework for doing information technology and how you wind up treating energy efficiency and energy productivity as a data set that's comparable and transparent between companies, same way we treat quality. Work with our small businesses and also work with combined heat and power. On our facilities, this is our R&D consortium. So why does this matter? Again, going back to Henry Ford as a model on this, if Henry Ford had an innovation, he literally owned, and I'm saying he, an individual, had ownership all the way from a mine to the dealerships. So in the terms of an economist, if you could wind up getting an R&D innovation, they could appropriate the value from it into his own organization. We don't live in that world anymore. Due to our, I wouldn't say due to our friends, but anyone here from GSB? Before I throw the MBAs under the bus here. So we financialized the economy at this point, where you've got OEMs and then you've got tier 1, tier 2, tier 3. There's a good reason for doing that. By being a supplier, you can be the best supplier in the world of a raw material and supply the entire industry as a result. There's economies of scale you can wind up getting out of that. The challenge is then when you wind up having a research and development innovation, where as a result of that innovation, the value is achieved in the supply chain, in the OEM, in the customer, how you wind up putting that together, no one can afford to do that research and development by themselves. How do you bring them together? How you can get them to work on a problem together? Broad recognition on this. The semiconductor industry, literally right down the street, figured this out 30 years ago. They all came together and they formed something called Semitech, right? It's a research consortium where you can have Applied Materials and Intel, all these companies working together, the photoresist suppliers, that they can work on a common set of problems together on pre-competitive research and development, that then can wind up rolling out if it's successful. So how are we doing with some of these public-private partnerships? So what I'm gonna point out is for a problem that really is a challenge in terms of your economic competitiveness. And that's the use of rare earth materials in clean energy. So the global market for rare earth materials is a $2 billion market, which sounds like a lot, but as far as raw materials, a pretty small market. So what we need is technologies where the problem is those rare earths are key to magnets, which are key to motors, which are key to electric vehicles and conveyance, right? Those are trillion-dollar markets. So how do we do R&D together? We're looking at applied research and development to diversify the supply, develop alternatives, improve recycling, and build that foundational research all together on that. So this is actually led out of Ames, Iowa. It's Ames Lab, Oak Ridge, Livermore, and Idaho National Labs. There's 7 universities as partners on this that are all working together on a coordinated research and development program together. In 3D printing, actually through our national lab systems, we have tremendous material science capability. What we wound up doing is setting up down at Oak Ridge, and they also partner with the folks at Livermore, the ability to have companies come together where it's the equipment suppliers, the material suppliers, the end users, all working on research and development together around 3D printing. I think the highlight of this is what we're showing down in this lower picture, where one company came along, developed a large area 3D printer for carbon fiber reinforced thermoplastic materials. Thing winds up printing 40 pounds an hour was the original spec. Wound up over 100 pounds an hour it can print. They worked with the materials developer to develop new polymer blends that can wind up working on that. And then in came a startup company that said, hey, we can 3D print entire cars. So that's actually a 3D printing of a car that's in that area. If you think about it, you can put together an entire factory to build those cars for about $10 to $15 million. You can produce 500 to 1,000 cars a year that way. You compare that as a capital efficiency to a $1 billion to $2 billion plant producing 100,000 to 200,000 cars a year, and suddenly you say, wait a minute, the return on capital isn't the right neighborhood. We can actually wind up doing this customized vehicle potential out there, but we need that technology breakthrough. We also do a lot of work in metals. How many people here are material scientists? I'm a material scientist? Okay, so that's a neutron tomography image inside of that, where you're looking at the 111 crystal orientation of a nickel-based superalloy, where you're able to actually program into the internal structure of the materials what the grain structure is. It's a huge breakthrough as far as what's happening. What it suddenly means is all your mechanical engineering friends, instead of just worrying about external surfaces of something in their design software, now you have to have the data tools to deal with every internal surface as well. Becomes a design allowable. Complete change in what your thinking is about it, which then drives all the information technology folks that are actually designing those design tools as well. Huge breakthroughs that are happening in that area. Doing the same thing in power electronics. I think you heard my colleagues earlier talking about use of power electronics in vehicles. Wide bandgap semiconductors, silicon carbide, gallium nitride, that were actually some of them grown right over here by Jim Harris's group in 20 years ago. That research is now finally getting out to the point where you actually wind up scaling it up. Why this matters, these are semiconductors where you can actually switch high voltages, and because of that, you can wind up switching high powers. So you're not sharing just the information about energy, you're actually directly controlling power and energy as it's flowing through the wires. Completely enabling for things like advanced power grid, advanced vehicles, advanced buildings. Again, these are things that are broadly disseminated across the entire EERE portfolio and DOE portfolio. Composites, we're looking at the Advanced Composites Institute. This is looking at 7 states pulled together as a partnership on this, building a public-private partnership. Roland, I just saw you look at your watch. I'll be done in a minute, so. And this is based down in Tennessee. Again, the goal isn't to invent carbon fiber composites. We've done that. What we need to do is get that aerospace grade composite at the same cost point and energy point of what it takes to do and throughput as automotive level production. Huge technical challenges to be able to do that. Then the final one we're looking at is this smart manufacturing area, where we're looking at real-time process control, integrating that. We're in the middle of a solicitation right now for an institute on that for real-time control and sensors as an institute. We're looking at new technical areas. We're always holding workshops on that. Last thing I'm going to finish up on here is individual R&D projects. And just to give you an example on that, we do materials, we do processes, we do batteries, things like that as well, as far as the enabling process capabilities. We also do a lot in terms of capabilities for how you manage energy on a distributed basis within a manufacturing facility. So high efficiency stationary power sources for both turbine-based and land-based facilities. 2 things that are new that I want to point out. One is, if you look within the Department of Energy, we have access. When I started this pitch about a year ago, we had access to 7 of the 10 most powerful computers on the planet that were within our national lab system as high-performance computers. Right now, literally as of yesterday, we had 5 of the 12 most powerful computers on the planet. That number is constantly going back and forth where you are. But the question is, how do we unleash these for practical problems that manufacturers have that actually require the scope and the intensity of what you need as a true HPC problem? So you look at things like linking in the chemical reactivities and the CFD work, looking at turbulent flow in turbines, so you can wind up boosting turbine operation. Really hard technical problem. Looking at, again, how you get water out of fibers, or how you can wind up running things like steel mills and coking ovens more effectively. So we ran a solicitation. This was Livermore working together with Berkeley and Oak Ridge to make that computer time and partnerships with industry possible. Just yesterday, we announced the first set of 10 projects through a merit review process that are across the energy sector that we're working on that. And then the final program I want to talk to, and this is to the students specifically on this. So if you look at our national lab system and look at our university system, these are some of the brightest places we have in the world on R&D. But we're here in the middle of Silicon Valley. And if you think about it, someone starting an energy startup, you don't hear them saying, you know, I really want to work into a national lab to do an energy startup as a new student as their first startup. They wind up taking a crappy warehouse over in Hayward, and they're on their own trying to raise venture capital. How do we wind up changing that? How do we use these places so you can wind up building together better mentoring, better training, so you get a better chance at starting your company, especially in these long physical science-based problems. Most energy problems require a lot of physical science, a lot of capital capability. So we started last year a program calling Cyclotron Road that we tested over at Lawrence Berkeley Labs, where you wind up bringing in those innovators, and we have 6 innovators. One of the teams, actually 2 of the teams are from here at Stanford, where they wind up coming in, they actually wind up going through a mentored entrepreneurial training program so that they've got to, and keep them fed and keep the rain off their head and give them a desk for a year, because we spend a lot of money on R&D relative to energy. Question is, how can we bring the entrepreneurs into that ecosystem so as we're doing that, we're getting the best outcome from that? And that's the entire purpose of that program. It's a human capital development program. And getting back to what I said at the start of this, if you look at what's coming out of Paris, we've bet on innovation. That means we bet on innovators. So programs like this are how you wind up developing that talent pool of the next generation of innovators. So with that, if we're successful at this, what does success look like is we're not just inventing products here, but we're actually making them competitively here as well. So thank you very much. Roland?
Thanks, Mark. I think you might have figured out not only has Sunita been a teacher, but Mark has as well, and I have as well. So you'll find many of us at DOE were formerly in that part of the cycle. So I wanted to ask you a question. Sunita gave you a test. I'm going to give you a test too. Mine's pretty simple. Raise your hand if you live in or work in a building. Most of you got that right. Okay, that's good. It's a great start. So we're going to talk about buildings. And so why do we talk about buildings? So not only do you live and work in them, but let's look at the energy part of the building. 40% of the energy in the U.S. is used in buildings. You've got to look at it. You can see the other 2 sectors here. But what's not on this chart is over 75% of the electricity that's used is used by buildings. So you really have to focus on this sector. Now, one of the things that's the same with Mark and I, and we both work together on a lot of ways to use manufacturing into the building products. Let me ask you, how many products do you think there are in a building? It's not a PV, which is basically 1 or 2 types of products. Fuel cells, there's just a couple different kinds of projects. How many in buildings? Well, we track about 550 of them. So you can see that there's a whole lot of stuff we have to look at every day. Okay, when I try to explain the complexity of the market, I finally put this together because people just didn't understand what we had to deal with. Well, on the left, you have the residential and commercial buildings out there. And as you work across, you have to look at new construction versus retrofit. They're very, very different parts of the market. Then you have to look at the type of material used in the construction, because it has an impact on what sort of technology works or what sort of solutions you can use. And then if you keep going, you get to the building use. Well, multifamily is very different from single family. If you have a big box store, you can't compare what you do there with a hospital or a dry cleaner. They are very, very different sectors. So you have to look at all those pieces when you look at this market. And then you get to the right-hand side, and if you don't take into consideration climate, you're going to make a major mistake, because hot, humid Florida is very different solutions than Alaska or hot, arid Arizona. So then at the bottom, that's when we get to the fun stuff. This is the technologies. So those technologies have to apply differently in each one of these. So you can just do the math, and you can see how many combinations there are. Okay, so how do I look at it? Well, I look at it, there's 3 parts to my program. 1, the technology innovation, which is primarily what we've been talking about today. And Sunita did a good job of laying out, it's not only a tech innovation, you got to demonstrate it and deploy it. So I have that in here. Those are the first 2. I have a 3rd part. I have a regulatory part, which basically locks the floor on how that equipment performs. So we have the minimum performance standards for energy efficiency performance standards, and also we have building codes. Okay, what technologies do we look at? Well, I said there's over 550 that we track, but we went and did the QTR, it's chapter 5, and we looked at all the different things we're looking at. There are lots of things out there. What we did is we said, are there some big opportunities that we have not been addressing sufficiently? And we found that there were several, and those are in our proposed budget for 2017. One thing I did just recently is I started a sensors and controls, let's see if this has a pointer, sensors and controls area, because it is really foundational to everything else that we're doing. But we also have, we'll talk about this top one, and then decision science and miscellaneous electric loads are somewhat mentioned briefly in a minute. We've been spending about $25 million a year for over a decade on solid state lighting, and the results you can see in the market today. They are a major part of what you're seeing. Now let's look at what we did. Well, during that time, the efficiency of the A lamp, which is the one that you put in, you screw in like the Edison bulb in lamps in your home, has improved 85%, while the price has dropped 90%. Now, what about the, so I think that's great, but for me, it doesn't matter unless you get sales where you're actually getting the savings. So what about the sales side? In third quarter, according to NEMA, third quarter of 2015, 15% of all light products sold were LED. That's a 230% increase over the year before. And during that same time frame, CFLs dropped by 28%. So you can see the shift going on in the market. And if you look at where we are as far as efficacy, we are only 1/3 of the way to where we can go and where we want to go. So there's a lot of room here. You're going to see a lot more innovation. We look at technology innovation. We look at good information on the performance of the lights. And we work on manufacturing cost reduction. We actually have a mandate of U.S. production. If we fund something, we want to see substantial manufacturing in the U.S. based upon that funding source. Okay, what's the next big thing that we're looking at? This one is huge. If you look at HVAC, it's a large percentage of the market. And yet, the innovation which we've done some great things in this space. There is a major change going on in the next 5 to 10 years, and I'm going to tell you a little bit about it. So it's driven both by efficiency, but also by environmental factors. So there's some new rules out on what levels of global warming potential cooling fluids can be used in equipment. Now we're talking about equipment that's in the market today, and there's new rules going into place. So we're looking at two parts to this program. One is replacing the existing cooling fluids with ones that are lower global warming potential, and we've got a lot of work going on in that space. But the one that's even better is, what if we had equipment that didn't need any global warming potential cooling fluids? Sounds good? And it's more energy efficient. So that's what we're really focusing on, and I'll give you a couple examples. And what I like about it is it's IP. This is intellectual property that doesn't exist anywhere today. So if you have a company doing this today, where are they going to manufacture it? They're going to want to put it where they have close hold on that technology. So we're really trying to drive manufacturing back into the U.S. for technologies that are now ubiquitous across the world, and so they can manufacture them wherever they're cheapest. One of them, we have a lot of different ones we're looking at. This is a magnetocaloric. Basically, if you take a magnetic material and you put you try to line up all the magnetic material in one north-south pole, it actually is heat producing because it doesn't want to be that way. It wants to be random. So if you do that, you actually create heat, and if you release it, you create cool. So pick which one you want. Do you want heat or you want cool? You grab that and you run forward. So we did this with Oak Ridge and GE. We did it for a refrigerator, and it worked. Actually, it did the freezing. I didn't think it could get the freezing. It does fine. GE says they're going to have this on the market by 2020. Of course, my wife said, well, what's going to happen? Are you going to have less space in the box? Answer is no. You'll have more space for food because the way this can be configured, you don't have that compressor and all the things associated with it. Here's another one. This is based upon work that Sunita's team did on fuel cells. This is a small company called Exergy that basically took a fuel cell, and she described how the proton moves across the membrane. Well, this is sort of a fuel cell in reverse, and it creates a heating, cooling opportunity again. So this is one this product is being sold, actually it's being built by GE for water heating, but it applies to many, many other products. So you're going to see this, another shift in the market. and we're funding other things like this going forward. I always said, why don't we innovate on drying? We heard Mark talked about drying before. So Oak Ridge came up with an idea, and they said, let's use ultrasonics. You basically take a piece of cloth, you soak it. We did this. You can see the picture. You soak it. You stick it on a ultrasonic transducer. You hit the button. There's a puff of water vapor. You pick up the cloth. It's dry, and it's not hot. Think about that for your drying cycle. So now we're trying to figure out how we can make that into a product. Sensors. So you heard me talk about sensors and controls. What I think about sensors is as a platform. I want a low-cost platform. Sensors today are like $150 to $200. That's ridiculous. I told them I wanted $10 to $1. So we actually came up with a platform. It's works for, it's self-powering. It's got some 2 or 3 day storage. It is, it measures relative humidity, temperature, and light. We're going to be working on occupancy and indoor air quality. We did a crater with Molex. They're the ones that put all the sensors in your smartphones. And they said, we want to get into this new business. We want to make this a low-cost solution. Look for this. We'll skip that one. So homes. We're going to talk more about this later, so I'm not going to say a lot about it, but I want to tell you that my vision for a home is that it should, or building, it should be self-commissioning, self-configuring. It should be self-learning. It should know how it's performing and fix itself if it can. And if not, it phones home for help. And then we want to be able to connect that with the grid to provide services to the grid. Again, we'll talk later. 2 different areas. The top one is hardware. The bottom one is software. We're using sort of market-based solutions where it's sort of a crowdsource. And we use the national labs for technical expertise. And we'll let companies or people come in, propose their ideas. We give them technical advice and support. And then we move to the next stage, which in the hardware side, there's 3 industries that are saying we want to take that to market if we like it. So it's a great way, again, to speed the innovation. This is my market, sort of the market support slide. And the point I make is we have 4 things we typically do. One is to do a technology challenge. Second is demonstrate. We do adoption campaigns, and then we just provide support. An example is the RTU, where we took a commercial air conditioner that was not available anywhere. We put a spec out that was 50% more energy efficient than anything on the market. The manufacturers, some of them said yes, some of them said this isn't going anywhere. Now they've changed their mind. Now all the major US manufacturers build 198 products that meet this spec. We have 45,000 products that have been sold in the last 2.5 years that are either brand new or in a renovation of existing equipment and saving, you can see how much money. This is then rolled into the standard that just went into place, just was announced at the end of the year in December. So this shows how innovation, market uptake, and standards all link together. Okay, only thing on this slide is I wanted to make sure I got some of the student side of this. We have zero net energy residential and commercial programs. This is one where we've taken what we're doing in solar decathlon, and we're actually changing solar decathlon going forward. But this is looking at students. We have 37 student teams coming in to design a zero net energy building. And the building is spec'd by a company that wants to build it. So it's actually not just a classroom project. This is an opportunity for the teams to build something that someone wants. So it really brings together the architecture, engineering, and the energy side all together, which is something we've been looking for. This is going to happen in 2 months at NREL. And again, it allows the teams to compete, and then they get selected, and then their designs get used. The last thing is we have, so this is a shameless pitch. We have lots of opportunity in the program. We'd love to have people who are interested in this area come and join us. Washington, D.C. is nice some of the year. So, no, that's not. When I got to DOE, Steve Chu called me into his office and he said, what would you do about this building? And I said, one word, C4. With that, I will close, and thank you very much. And I guess we have 15 minutes for questions. Any questions? Some in the back?
In the beginning, you have a chart showing one technology about this electrical caloric effect, and you show a chart for 4 different types of technologies, right? And there's one class called this electrocaloric effect.
Oh, yeah?
So could you say something about that? What kind of status, state of art technologies?
So we actually have about 12 technologies that are in that space. They're non-vapor compression technologies that do heating and cooling. And we've got probably 5 of them we have small projects underway on. The 2 I mentioned, the electrochemical and the magnetocaloric, are ones which have moved from the lab into a company that's building it. The others are still being designed. There's one which is looking at putting metal rods into tension, which heats them up and then releases it, which cools them down. We have multiple ones, but we have a funding opportunity that's out on the street that we want to fund new ideas. And for FY17, we're opening it up even wider for new ideas that we can actually take past the demonstrate that it works, and then get accredited with a company who actually put it in the market. Because as I tell the labs and the performers, if you prove that something works, it doesn't really get me anywhere. Unless you get it in the market where it's actually creating the value, that's when I say we have a win.
Hey, Roland, if I can jump in here also on electrocalorics, this is actually an area on the caloric effect that both the building office and the advanced manufacturing office are decided to work together on a program over the next year. When we started looking at that, we realized one of the rate limiting steps is actually the current state of the art of the materials. We do have a set of materials that show giant magnetocaloric effect and electrocaloric effect. We've got proof of concept demonstrations, but if you look at the big potential for moving forward, it's actually going back and saying, how do we really understand those materials better? So as part of the Energy Materials Network that Ruben spoke about earlier, it's actually based out of Ames, but it's partnering with, I think, 6 different universities. The electrocaloric effect work is actually with the folks at Penn State that are doing the polymer electrocaloric effect. If you look at the nature of the technical challenge that you're trying to address in a lot of these, it's having reversible phase transformations between low entropy, high entropy state, ferromagnetic, paramagnetic state kind of thing, let's say for magnetocaloric. How do you get that phase transformation so you don't wind up having defect formation that becomes degradation in the long run? So understanding that it's very applied research and development, but it's definitely materials research and development that we're working on as a result of that. So that's kind of where we're pushing on that. I would encourage, if you're interested in that research, on this, is reach out to those points, because the purpose is to then having a place where we can wind up having critical mass, having researchers from universities work together with the labs together on that is a key element of continually growing that ecosystem.
In the back?
A lot of the new business models on energy efficiency depend on baseline measurements. Is that something you're working on as a review?
Yeah, so that's always a challenge, is what's the baseline? There's a couple answers to that. I think someone mentioned EIA, I think it was Mark. We use EIA when we can. Otherwise, what's out there in the world is really models. So we actually have a project underway with LB&L, with their Flex Lab, to basically put some empirical data around the model assumptions that go into a lot of that baseline work. So we're actually building that empirical data that will be pulled back into the model. The models we use are Energy Plus. Energy Plus is probably the top physics-based energy model in the world. And it's actually now being used by Autodesk, Carrier, Trane. I can go down the list of everyone that's using that, largely because we went from having it an academic model to making it a market-based model where we put OpenStudio on the front end so people can program it. So to answer your question, we are working on that. We have to we have to go beyond models if we're going to get these baselines right. Yeah. The other thing to say about baseline is we're using energy use intensity as the macro metric for performance in buildings. It's something that crosses any country or any type of building, and that's been a big shift I've had to push through the program over the last year, but it's now part of our plan.
And that's also why both our portfolios are investing a lot in sensor technology. Yeah. Because you can have all the right protocols and methodology, but if you can actually cost effectively get the measurements in, you're not going to be able to widely disseminate that capability of doing that baseline measurement.
Jim.
Roland, if you look at commercial buildings, one of the ongoing problems has been the split incentive between the tenants of the buildings and the owners. Yet there's been very significant changes in some areas where, say, the Empire State Building, for example, which is where they found that 2/3 of the savings were in the tenant spaces, and new contractual structures, new collaborative agreements were being forged. Are you doing research in those sort of behavioral measures that are causing existing technologies, efficient technologies, to be implemented in tenant spaces in those buildings?
So our Better Buildings program has pieces of that, Jim. I think the main thing we're looking at there are what models have been used in the market, and then how can we provide data to allow other people to put those policies or programs in place. It's largely why we work with cities a lot, because a lot of that happens on a city scale. It's not going to happen on a national scale. The country is too diverse. But a city can actually put some of those policies in place as long as they have the right information to allow them to make that decision. So again, Better Buildings program has a piece that's doing that. Other questions? I thought I saw some hands.
Not over in the students.
Back over here.
Thank you. You mentioned that there's 87 billion square feet of office and industrial space. How much of that is government, federal and state, and what programs do you have to make sure that these great efficiency technologies are deployed quickly and first in the government buildings?
So we didn't put up the official org chart. So in the energy efficiency branch of EERE, there's two other offices. There is the energy efficiency and is the Federal Energy Management Program, FEMP is there, and our colleague Tim Unruh runs that. And then the weatherization program as well, and the state energy programs are together as a program together in that area. And those are the areas where we're really trying to drive forward those energy practices in a lot of the federal spaces. I think Roland can probably speak more to that, but a lot of the sort of the contracting vehicles that's knocking down the sort of the really hard bureaucratic issues we have to get to, so you can actually get a contracting structure to be able to do those sort of things.
Yeah, actually, let me follow up, and I'll let you ask your, but really the technology and the solutions are the same. The building doesn't know whether it's a federal employee in there or not, or private sector. So Tim, the chairman, the director of FEMP, and I and our teams actually work together on a lot of these. The difference is how it gets implemented. The private sector is actually easier to work with
Hard to believe that.
than the government, whether you believe it or not. So we have to use different techniques to get something in the government sector. Happy to talk to you offline if you want to go deeper. But you had a follow-up question?
I was just wondering how deep and what percent implementation do you have in those federal buildings?
Well, let me just give you one example. So, it's different for different sectors. So actually, DOD does a pretty good job. They're fairly aggressive because it's sort of built into their mission to be able to be on their own no matter what. And so they really have a pretty good grasp of how to move forward. So we have get a lot of progress with DOD. Some of the other agencies, not so much. I'll give you an example. So there was an executive order that said buildings should have metering. Imagine that, so that they know how much energy they're using. Well, but there's an out. If they claimed that there was a national security reason why not to, they didn't have to. Guess what? Most of them said we think it's a problem. So that's the kind of issues we have to work through. So we're now trying to come up with solutions that allow them to do some of that metering without creating issues for their energy security. That's just one example. There's lots of them. Okay, anyone? I thought I saw a few more
We have
hands.
some hands right here in front.
Right here. Hi.
Thanks so much, and thank you for mentioning the importance of adoption of a lot of the technologies you're talking about. I was just curious if you do actual empirical research as well on what adoption techniques work, in addition to the campaigns you run to try to push these things out. Like, how much do you keep track of what works?
So it's a great question. So I came from a utility. Actually, it was a utility that Diane used to regulate. So we know this side of the world very well. And adoption. When you have a customer, and you get tracked M&V on how well that's working, you know kind of how that works. When you come back, step back to government. So government, it's hard for me to actually force adoption. It's hard for me to get incentives in place. I can't give money away. All I can do is give data or information or some way to allow people to reduce the risk of adoption. So that's really what we do, is we reduce the risk. So the commercial program is the one that I have the best success with. We have a little bit with residential. Happy to talk about that too. What do we do with commercial? Well, we call it the high impact technology approach. So we identify, and there's a way we I told you about the 500 some odd technologies. We rank those on the opportunity, both technically and market-based. And then we take that and we say, okay, which ones are we going to go after? Because you can only go after a few. You pick ones that have good potential. And then we go after those market sectors I put on that other chart and say, which ones of you want to work with us? If we don't have a market, there's no progress. And you get a market to work with you. So I'll give you an example. Went to Big Box and said, let's work on parking lot lights, parking and parking lot lights. And we put together a performance spec all together. Everyone agreed to it. They went out to the manufacturers and said, this is what we want to buy. Now, before that, there were thousands of specs, so every spec was individual, so it was very expensive. Now they're all competing for one spec. The price dropped dramatically, and we've sold hundreds of millions of lamps to that market based upon that spec and that campaign. So we do things like that. I can tell you more, but it's really a different instrument when you talk about federal government versus something local.
Can I ask, what's your actual research area you work in?
I do research in psychology on how to encourage sustainable behavior.
Okay, so this is actually one of the hardest problems we have within the government on all of our programs, because what's the control group you're comparing with, right? So we get adoption out there. So retrospectively analyzing this as a research problem is a really hard problem. It's a great data problem to work on. I will give you a comparison here relative to the university. I am certain the university loves to publish statistics about here's the number of students that have gone to Stanford University and here's the outcomes of their life. They don't go out and they look at that second control group of people that applied to Stanford and may have gotten in even, or just applied to it as a control group, and what's the differential relative to being at Stanford, right? So that's the problem you're trying to study, is saying, what's that control group? Now, we actually did this last year working with SRI on one of our programs where we said it was looking at an energy adoption program where we had 40 years of data, and we had SIC code of the company that was being worked with and the zip code. You could actually then go out and data mine and create a quasi-control group of companies that had similar profiles and then see a differential comparison relative to those two. So it's actually an area where there's huge opportunity in the data science side. By the way, not just in the Department of Energy, across all of government on how we actually track what we wind up doing. So I think as a research area, that's a very fresh area to be working on.
And ours is more macro, where we say, what was the adoption rate before our program, and then what was the adoption after? It's sort of the macro view. And we have that data on the initiatives we put out there. More questions? There's one, Dan.
One of your great programs is the Energy Efficiency Standards Program. You referenced it briefly, but it can be a controversial program, as you well know. What's the politics these days in Greece for that program sitting in Washington, D.C.?
I'd step off the stage.
you just loved doing that, didn't you, Dan? So I think what I'd tell you is some of the standards are loved by everyone, and some are really a challenge. And we have some of the standards which have politics around them regardless of whether they're valuable or not. And the example I'll give you is the one on lighting. So I got a chuckle from someone who knows it deeply. So the challenge is this. We were told in legislation to put out a standard for general service lamps. Subsequent to that, and there was a date given that we had to start it, and actually we have to deliver it by January of next year. Then we have language in our budget that says we can't spend any money on general service incandescent lamps, and it's more of a political issue, not a technical issue. The manufacturers have gone up to the hill and said, what are you doing? We want this to go forward. But the politics are, no, we don't want a standard. So what's going on right now, and I could talk about what we're trying to do to solve it, but what's going on right now is since we can't touch general service incandescent lamps, I can't spend money on putting a standard in place, there's something called a backstop provision in the legislation, and that backstop provision says that by 2020, if the lamp doesn't meet this performance spec, 45 lumens per watt, you can't sell it. Well, guess what? In that category, there isn't a single product that meets it, and there's no projection that any of them will meet it. So you can see the train hitting the wall. So what are we doing about that? So I'm actually doing a technology play trying to figure out how I can get the market to move faster in that area. And so that's interesting because the market's telling me these are niche lamps and it's not worth a lot of spend on our part to go after this niche market. We just as soon abandon it. And then I look at the consumer side and say, wait a minute, if you've got those 2-pin halogen lamps in your kitchen and nobody's building a lamp to replace it, and you go to the store in 2020 and they say, sorry, you got to buy a new fixture, right? That's not going to be a happy game. So that's, you asked about the politics. I'm giving you one small piece. There's another one I'm sure you were thinking of. I avoided that one. So I'm, are you smiling? So that there is a lot of politics around this, and we just have to keep going forward and doing the best we can with the technical data we have and the rules we have built into legislation. Diane.
Brought up another part, the Clean Power Plan. So I guess there's before and after the state. But is there any effort that your office is doing given the importance of energy efficiency in the state implementation plans that we file? Any specific focus that your office has on helping the states, the regulators, the quality agencies, or the utilities on more uptake and more use of energy efficiency?
Okay, and I'm told this is the last question. I got the time. So yes, we are. We know about the problems. We're actually working very closely with EPA, who has the Clean Power Plan. In fact, a lot of the folks that are over at DOE were in the team that now has the Clean Power Plan for EPA, so they're on my team and Kathleen's team. So what are we doing? So multiple things. One, through C-Action, we're doing some initiatives sort of focus on state-level solutions. One which most people don't know about, but I think is really exciting, is a year ago I put in place a FOA for the residential codes program where we went and we funded 8 states to have them set a baseline for how well their code adoption and compliance was actually delivering quantified savings in the market. And now we have multiple states joining in on their own nickel to do the same thing because they're looking at the future and they want to have some way to quantify what they might do. We're releasing a FOA shortly on the commercial side. It's much more complicated, so we're doing a sort of a first step in that space to sort of figure out how to get at that market. But for that same reason, we're trying to figure out how do we provide some sort of quantification to allow, and it's state by state, to allow states to use this as a platform for meeting the CPP rules. And there's other things as well, but those are from my program. Sorry, I think we're out of time, but Mark and I are going to be here all day, and hopefully there's some questions you can ask us in person. So I don't know who's got this next. What's that?
Doug.
Doug.
Okay.